If you separate positive and negative electric charges and put them into boxes, the bunch of negative charges forms a minus pole and the bunch of positive charges forms a plus pole. A voltage is created between the negative and positive poles. The voltage is abbreviated by the letter U and is sketched like this, for example. The voltage tells us how much kinetic energy a positive charge would gain if it traveled from the positive to the negative pole. Voltage is measured in volts, abbreviated with the letter V. Let's assume that there is a voltage of 10 volts between the poles. We can't do much with voltage alone. Next, we need an electrical conductor. This could be a wire made of copper or aluminum, for example. We need this conductor to connect the two poles with each other. Of course, it makes a difference whether we use copper or aluminum for the connection, because different materials conduct the charges differently. But more about that later. Since the two poles are now conductively connected, the positive charges can move to the negative pole along the conductor. They are eventually attracted by the negative charges. Thus, there is an electric current I through this conductor. The negative charges, of course, would also travel to the positive pole. However, we have fixed them in the box so that they cannot move, in order not to make our thought experiment unnecessarily complicated. The resulting electric current I is measured in amperes, or short, amps, abbreviated with the letter A. Over time, the number of positive charges at the positive pole will decrease because the charges are moving to the negative pole all the time. Thus, the voltage and current would also decrease over time because fewer charges are separated. To prevent this, we will constantly supply the charges to maintain the charge separation. This resupply of charges is the purpose of a voltage source. With a voltage source, we make sure that the voltage and current stay constant and don't get lower. Let us assume that a current of 1 ampere flows through the conductor. Our voltage between the poles is set to 10 volts and a current of 1 ampere flows. Now let's change the voltage and see how this affects the electric current. We can change voltage by changing the number of separated charges. If we increase the voltage from 10 volts to 20 volts, then the current increases from 1 amp to 2 amps. We have doubled the voltage U, and thus the current I has also doubled. If we increase the voltage from 20 volts to 60 volts, then the current increases from 2 amps to 6 amps. We have tripled the voltage U, and thus the current I has also tripled. If we decrease the voltage from 60 volts to 40 volts, then the current decreases from 6 amps to 4 amps. We have decreased the voltage U by the factor 2/3, and thus the current I has also decreased by the factor 2/3. No matter by which factor we change the voltage, the current also changes by the same factor. We can illustrate the measured values in a diagram. On the y-axis, that is the vertical axis, we plot the voltage. And on the x-axis, that is the horizontal axis, we plot the current. This diagram is called voltage-current diagram because it illustrates the relationship between voltage and current. Let's plot our measured values. At 10 volts between the poles, 1 amp current traveled through the conductor. At 20 volts, we had 2 amps. At 60 volts, we had 6 amps. And at 40 volts between the poles, we had measured 4 amps. If we now connect the measured data points with each other, we get a straight line. Whenever a straight line comes out on a plot, then we say that the plotted quantities are related linearly to each other. So we have found a law that voltage and current are linearly related. And this is exactly the statement of Ohm's law. Ohm's law says that if we plot voltage U as a function of current I, we get a straight line. What if we plot our voltage and current measurements and get such a curved graph? Does this conductor fulfill Ohm's law? No, it doesn't, because it is not a straight line. A conductor fulfills Ohm's law only if the voltage-current graph results in a straight line. An electric current through such conductors, which give a straight line, are called ohmic conductors, because they fulfill exactly Ohm's law. For example, a conductor made of copper is an ohmic conductor. This is because if we apply a voltage to the copper conductor and a current flows as a result, then the current and voltage are linearly related. The straight current-voltage line is represented by its slope. We denote the slope as electrical resistance and abbreviate it with the letter R. We can therefore say, a steep straight line has a large slope and thus represents a large electrical resistance. A shallow straight line has a small slope and thus represents a small electrical resistance. So far so good. The slope corresponds to the resistance R. But what effect does the slope of the straight line have on the voltage and current? A shallow straight line, that is, a small resistance, means if you increase the voltage U only very slightly, then the current I increases very much. On the other hand, a steep straight line, that is a large resistance, means if you increase the voltage U only very slightly, then the current I also increases only very slightly. How can we now unite the three quantities, voltage U, current I, and resistance R, in one formula? Let's use the language of physics, that is, mathematics, to translate the straight line into a formula. From mathematics we know that a straight line passing through the origin of the coordinate system is described by the equation of a straight line, y equals m times x. M is the slope of the straight line. In our case, the slope is the resistance R. So let's replace m with R. The y is at the y-axis and is the voltage U. So we replace the y with U. The x is on the x-axis and in our case represents the current I. Let's replace the x with I. And we have a straight line in the diagram translated into a formula. So Ohm's law as a formula is U equals R times I. You can find out the unit of resistance from the formula for Ohm's law. You only have to solve the formula for the resistance R. Bring I to the other side and you get U over I equals R. Or just written down the other way around, R equals U over I. The voltage has the unit volt and the current has the unit amp. The resistance must therefore have the unit volt per amp. We abbreviate volt per amp briefly with the unit ohm. By the way, this character is a Greek letter omega. The value of this electrical resistance R depends on the conductor used to connect the positive and negative poles. A conductor made of iron has a lower resistance R than a conductor made of copper. For the iron conductor, we expect a shallower straight line than for the copper conductor. And a conductor made of copper has a smaller resistance R than a conductor made of aluminium. So an aluminium conductor has a steeper straight line than a copper conductor. Let's take a look at some concrete examples of how you can apply Ohm's law formula. First example. The voltage between the poles is 10 volts and the current flowing through the conductor is 1 amp. What is the resistance of the conductor? For that, we solve Ohm's law for the resistance R. R is equal U over I. Then we insert given values, 10 volts over 1 amp, and this is equal to 10 ohms. Next example. The current flowing through the conductor is 2 amps, and the resistance of the conductor is 100 ohms. What is the voltage between the ends of the conductor, that is, between the two poles? Here we can use the URI formula directly. U equals R times I. Insert given values. 100 ohms times 2 amps is equal to 200 volts. And the last example. The voltage between the ends of the conductor is 6 volts, and the resistance of the conductor is 2 ohms. What is the electric current through the conductor? To determine the current I, we solve Ohm's law formula for the current. Then we get I equals U over R. Insert given values. 6 volts over 2 ohms is equal to 3 amps.